Welcome to Finite Element Methods. We'll be discussing the application of numerical integration to 1D finite elements. In the previous lectures, I showed you how we can use Mathematica to integrate probably complicated expressions from -1 to 1. And the Jacobian may be a rational fraction that's multiplied to more complicated expressions and may require complicated integrals. So we need to find a systematic way to apply numerical integration. Now recall that we're talking about solving partial differential equations over a complicated domain in a systematic manner. And the biggest mathematical miracle we've accomplished in the previous lecture was to take a element formulation that's formulated over a arbitrary shape element or length. And that's a lot of work because you have to calculate the shape functions, the derivative of those shape functions, and the integrals had to be calculated over a domain that has arbitrary limits. But I was able to perform this mathematical miracle where every element is turned and mapped into an element that goes -1 to 1. And the powerfulness of that is that every integral goes -1 to 1. The shape functions go also are the same for everybody. And the derivative of those shape functions are also the same for everybody. So that simplifies everything a lot. However, the thing I have not discussed is how to deal with the numerical integration aspects. So the advantage of integral limits, we go from -1 to 1 for every element. That's great. It allows for simple numerical integration. And we'll be using the Gaussian quadrature approach, the Gauss quadrature approach for numerical integration. You may have seen this in calculus, but the trapezoidal rule, for example, evaluates this function at A, evaluates the function at B, and then basically calculates this area of this trapezoid. You have the midpoint rule, you have Simpson's rule. All these formulas attempt to find the integral of this curve between A and B. That's what they're trying to do. And I'm not going to spend too much time on this one because we're going to work on in one that I love that's used a lot in by abaqus and a lot of finite element software. It's called the Gauss quadrature. So you have the integral that goes from x1 to x2 f dx. My goal is to convert this integral using a change of variables. So it goes from -1 to 1 phi deep c. Notice here how I did the change of variables. I have f dx, f we're changing to x c, and the dx becomes j deep c. So I call this whole thing, this whole coefficient, I'm calling phi deep c, and that's why you see this transformation being made. Now my integral goes from -1 to 1. So how do we evaluate this integral? There is a table of values, and you can see here that phi deep c is approximately equal to this, and you can find these quadrature points. They're given to you, and the locations where to evaluate them. But in essence, I can solve the integral from x1 to x2 f dx by converting that from -1 to 1 phi deep c, and then using this idea of weights, quadrature weights, and then these phis are selected, and they're selected from a table, and they're evaluated at these particular points in a they're provided in a table. So what does that table look like? So so again, I'm looking at W1 here and where phi should be evaluated. So W1 and C1 is what we're talking about here. So for one quadrature point, C is evaluated at 0, and the weight is 2. That can solve a linear polynomial. A value of 2 is 2 quadrature points, and the weight is 1. And it can solve a cubic polynomial. So it can actually do a very good job. Just with 2 points sampled in that domain can actually solve the problem very accurately. or exactly. For three quadrature points, you're looking at solving the problem fairly easily after fifth order polynomial. Let's look at an example. I think it's helpful to look at an example of something you've done before. So say I want to find the integral with two quadrature points. So what is it? The question is, what is the integral from 0 to pi sine x dx? I think that's easy. What is the integral sine x? This integral sine x is cosine x. Um, and minus cosine x. It varies from 0 to pi, so cosine at pi is minus 1. Cosine at 0 is 1. I have a negative sign in front, so that gives me 2. Minus 1 is 2. So the integral from 0 to pi of sine of x is 2. Let's see if we can get to that value using this idea, Gauss quadrature. We need to transform the integral from minus 1 to 1. We have to go from 0 to pi to minus 1 to 1. So let's use the shape functions to do that transformation. So xc, this, and this is equal to pi 1 plus c divided by 2. Let's see if that makes sense. xi, in this case, is 0. So this goes away completely. Xj is pi, so I get pi times 1 plus c divided by 2. That's what I get. We can check it. C at minus 1, so c at minus 1 gives me 0, which is the bottom limit. C at 1 is 2 divided by 2 is 1, so I get pi, and that's the upper limit. So these shape functions do transform the element coordinates to the natural coordinates from minus 1 to 1. And remember, every single element is getting transformed in this manner. But we're just doing simple integrals, so you can see how it works. Now I have this dx. I have to change the variables, dx dip c. Okay, I can do a transformation and get pi over 2 dip c. Fairly simple. You can check it. Partial of x with respect to c. Okay. Partial of x with respect to c gives me 1/2 times pi. And you can see there, pi half dip c. Perfect. We have to put x, change it to c. So x is this whole thing, which you can see inside the integral here. And dx is pi half dip c. And my integrals go from minus 1 to 1. So I'm ready now to use Gaussian quadrature. So Gauss quadrature. So this whole thing inside the parenthesis phi, and phi, which is this whole thing, has to be integrated, has to be evaluated at the first quadrature point, which is minus 1 square root of 3 with a weight function of 1. You can see here that came from this table. C minus 0.5777 with a weight of 1. Okay? 1 over square root of 3 is that number, this number. It's the same thing. And then I evaluate this whole thing, but evaluate it at plus 1 over square root of 3 with a weight of 1. That comes from here as well. If I evaluate the whole thing, it's 1.94, which is pretty close to 2. In fact, it's actually pretty nice because it's not a small domain. 0 to pi is not a small domain, and I'm able to get pretty close. It's not too far. Okay. So let's look at how to integrate a polynomial that goes from minus 1 to 1. I already told you that quadratic polynomial, in fact, up to cubic polynomial, if I had a cubic polynomial with two quadrature points, I should get the exact solution. But let's integrate a quadratic polynomial. So I'll just take this as phi. Okay. So I'll take this as phi and evaluate that at the square root of 1 over square root of 3. And this one over the minus of that, you can see that there, with a weight function of 1. And when I do that, I get 0.3333. And when you check it, that's the exact solution. You get the exact integral value. If you did it in mathematics, you'll get the same value as using this approach. How you derive that? Like many people have asked me, where does this table come from? Like, how is that even possible? How does this work? It takes a little bit of work. I'll show it for interest purposes. So for n equals 1, let's do for n equals 1. So for one quadrature point. So let's say the phi, this phi here is a linear function. So I plug it in there, and I'll integrate that from -1 to 1. When I do that, I get 2a naught. Sure. So the idea comes as follows. So I already told you that for one quadrature point, I'm going to use this phi, and I'm going to evaluate a single value of C1 and multiply by the weight of 1. So I'm going to equate this. Now I know what phi C1 is. Phi C is this. So I'm going to plug in phi C1 here. And when I plug it in there, I have to equate that to a naught, 2a naught, which came from this integral here. And so that forces me to figure out how this compares to that. When I multiply this by that, I can now relate coefficients, okay? You can see here that the only way this equals to that, if its W1 is 2, and you can see here that C has to be 0 because there's no C on the left-hand side. So that forces this to be the quadrature point to integrate a linear function, okay? So that's how that quadrature point for n equals 1 was derived. For n equals 2, n equals 2, you get a cubic polynomial. Okay, so that's a cubic polynomial. Same idea. Integrate phi, you get this equation from -1 to 1. And guess what? It simplifies to this when you do it. I want to do the same thing. I want to find something with 2 quadrature points. So I have W1, and then I'll evaluate this up C1, and I'll take this and evaluate this up C2. And then I'll equate this to that and figure out how to put the coefficients together. So when I do that, when I plug in this and this in here on the right-hand side, I found the integral. The exact integral of a cubic polynomial is this on the left-hand side. Now I have to figure out how to relate this to this thing on the right. So you find that W1, for example, W1 times A naught plus W2 times A naught must be 2A naught. So that's that. That equation is that one. So you know that W1 plus W2 is 2. You also know that W1 times A1 times C1 plus W2 times A1 times C2, that has to be 0 because I don't see an A1 on the left-hand side. So therefore, W1 C1 is the minus of W2 C2. Then you can continue showing how the different coefficients match. On the right-hand side, I have A2. On the left-hand side, I have A2. So I should be able to match up. So I have W1 times A2 plus W2 times A2 C2 squared. These things are that equals 2/3 A2 on the left-hand side. A2 cancels out, of course. So you have this another third equation. And from the fourth equation, W1 times that plus W times that. On the left side, I have no A3, so that must be equal to 0, that addition. So C1 is a minus of C2. Now you have a system of equations. I have 4 unknowns, 4 equations, because I have C1 and C2 and W1 and W2. 4 unknowns, 4 equations. You can solve them. And when you do, you get a mathematical miracle. Is that W1 and W2 is 1, the weight function, and the C's are this. And the cool thing about that, and this is explained extensively in my book, but I thought I'll explain the derivation here. The cool thing about that is that this works out, and this actually can integrate a cubic polynomial, excuse me, exactly, which is quite incredible. So a Gauss quadrature here shows you what's going on. Where is the integral being performed? For 1-point rule, if I go from -1 to 1, for 1-point rule, C is 0, so it's right in the middle at C is 0. A 2-point rule will be exact integration for the problems we're looking at. M bold is quadratic, B bold is linear. So B bold transpose B bold is quadratic. So a 2-point rule should be exact at integrating this stuff. And yeah, a cubic M bold will give you a b-bold quadratic, which makes this quartic, and that will require a 3-point rule to get it to exact integration. So that's just showing you what order integration you need to really get the exact solution. So very cool idea here. And I did it quickly here for a quadratic element. Um, and actually, when you do it, um, when you do this using Gaussian quadrature, I invite you to do it. Since yeah, if you do it, you're gonna get the exact solution because we're using Gaussian quadrature with two nodes, two two Gaussian 2 points, two Gaussian quadrature points. Yeah, so I showed it here. I don't want to bore you through it, but you can check it at home. That when you walk it through this whole process, this integral here, you can see here, this integral here, as you work it through, evaluate it with the weight functions of 1 and 1 at psi equals minus 1 over square root of 3, all that will give you the exact solution when you do it. I have no questions. But if you were to do the same problem, say I want to use the same problem, the same integral I want to do, but I want to do it with n equals 1. Because you can choose what Gauss quadrature you want. N equals 2 is one possibility, but n equals 2 is one possibility, which gives you the exact solution. But I can use a lower integration. So I can just use 1 point, and I call that a reduced integration if I do that. So for that, I want to evaluate a 2 with a weight and C a 0, right? This is coming from that table here, if you're wondering. That's coming from this table. For 1 is 0 and 2. For 2 is this here, right? So I can evaluate it at whatever I want. It's going to be an approximate, right? It's not going to be exact. I call that reduced integration. So if you put n equals 1 and you evaluate the whole thing, you get this matrix here, which is quite interesting because I had a quadratic element and it turned into this. So a quadratic element with one Gauss integration point, interesting, leads to a no stiffness associated with the middle node. There's nothing going on in that middle node. This element will be unstable with one integration point because it gives you 0 and a column of 0. And so the strain energy does not depend what's going on with the middle node, only the endpoints. So that shows that the element will be unstable. It will be completely unstable. Actually, you can look at that if you calculate the strain energy for this element. It's only going to depend on the end nodes, which is interesting. So this is something that's going to come up later. Reduced integration is used when you cannot integrate the element exactly, and you're trying to use a lower element, lower Gauss quadrature integration point. But generally, you want to use this procedure. So if you have a quadratic shape function, then 2-point rule makes sense as you go through the calculations. And if you have n-bold linear, which happens with linear elements, then a 1-point rule is just fine. But anytime you are talking about, I need a 3-point rule to solve a problem, but I'm using a lower order Gauss quadrature rule, then you're really talking about basically, you're talking about reduced integration. And you may want to be careful because you could be introducing errors. So with that said, I want to thank you for listening to this particular lecture. I think it's very exciting that we can take a government equation, divide the domain. I don't care what shape, I don't care how you divide the domain, because at the end of the day, I plan to take every element and I plan to map it to standard element size. And this case goes from -1 to 1. And the integrals go from -1 to 1, which allows me to use this Gaussian quadrature approach. So to numerically solve integrals. So I have a way of doing that. I have a way of converting the problem into a standard element. Shape functions are the same. The derivatives are the same. And it's incredible. The only information that contains the geometry is the Jacobian. And that's a mathematical miracle because I'm now able to solve systematically governing equations with different element sizes, and not have to rederive the shape functions every time for every single element, not have to figure out how to do the integral for limits that change from element to element. I can just look at the standard element and solve it there and then assemble it for everybody else. Okay, so that's exciting. Thank you for listening.